It's not a now projected there as well as a example. Thing of putting it into presenter mode here and then sharing. But that's maybe like
Then it's usually either click or these arrows.
earlier you had the little laser pointer thingy. That might be useful to have.
Hello, everyone. Welcome to the Geotalk. Are we waiting for everyone? Do you have your Geotalk buddies with you? Okay, good. This week we have our talk by Jörn. So would you like to give a short bio about your specialty and why you're here?
Yeah, hello everybody. I hope you can hear me well if I'm standing straight. That's a very good thing. So I want to talk about today about basically these volcanoes that are often considered a little bit of odd type compared to like alkaline volcanoes in subduction zones, for example, in the Andes and so on. And hopefully convince you that they are not as odd, but actually quite important in a lot of aspects, and that this work is somewhat advancing our understanding of these type of volcanoes. So my background is actually really in this part here, in geochronology. And for the longest part of my research career, I was looking at uranium-lead geochronology. So looking at the isotopic, the radioactive decay of uranium to the stable decay product lead, and using that as a chronometer, like Scott is doing, for example. Where is he? Is over there. So we were doing a lot of sort of similar type of work. And that's a really great isotopic system because you can basically use it over all of Earth history, from 4.5 billion years ago, sort of the inception of the accretion of the planet, to almost today. And I'm saying almost because the uranium lead system somewhat fails us over the last something like 300,000 years. And arguably, you can say, okay, that's such a tiny fraction, you just ignore that part. But on the other hand, these 300,000 years are very important because this is, at the end of these 300,000 years, this is where we live. So looking at the very recent history of our planet, it's probably rather important. And we can utilize a different isotopic system that is also based on the decay of uranium, and using thorium, especially 230 thorium, the isotope 230 thorium, as that is an intermediate daughter product of the decay of uranium to lead. And we can look at the disequilibrium in that decay chain and use that as a chronometer. The background image here is a satellite image. It doesn't project particularly nicely. It looks a little bit nicer on the screen if you want to see it later. This is essentially all clouds over the Mediterranean. Italy is somewhere here. This is the coast of Italy. And this is Mount Vesuvius, one of the probably most famous volcanoes on Earth, and probably the most hazardous volcano in Europe, at least in Europe. And we will talk about this volcano much more later on when I introduce you to the work that we've been doing on garnet. And garnet is, of course, a very well-known mineral, not so well-known as a mineral in volcanic rocks that we will also speak about later. So thanks to Karen and Scott and Robin for the invitation to give this talk. I'm sort of on holidays, but I thought I pass by to tell you a little bit about this work that we've been doing. So of course I was not doing this all by myself. As you know, this typically collaborative projects. This was at a pizzeria, of course. When you do field work in Italy, you eat a lot of pizza and pasta. And this is the Pizzeria Magma, with a nice view from the terrace to the volcano here in the background. This is Mount Vesuvius in the background. So the main collaborator is actually Francesca Forni here with a face mask. At that time, Italy was still quite strict about wearing masks, especially in public transport. Then Marcel Guillon, the gentleman here in the green jacket in the background, he's the head of the laser ablation ICP-MES lab in Zurich. And then Roberto Sulpizio, this gentleman here, he's a very well-known expert on Vesuvius and did a lot of the work on the physical volcanology of the volcano. So without him, we probably would have just not found the outcrops and could not have done this work. So that's the core group of this project. So alkaline volcanoes, as I said in the beginning, they're a bit sometimes considered sort of the odd volcanoes. Some even make carbonatites. Some make phonolites that have sort of funny mineralogies. But if we think about them a bit more pragmatic, they're actually very predominant in intraplate settings. And that can go from rifts like the East African rift, where especially in Tanzania, you have very, very alkaline volcanoes making nephelinites and all the way differentiating to carbonatites. Then in hotspot settings, like for example, on Tenerife today, you make very alkaline volcanic rocks, but also in back arc settings. That's sort of where we are here with Vesuvius located in sort of a slightly extending back arc setting. And they can produce very hazardous eruptions, as we will see in a minute. The volcanoes that are important here, and this is probably the most important aspect in a way, that these volcanoes, because they're intraplate, they're in the middle of a continent, this is where we live, and they can produce very big eruptions that are probably very often very close to human settlements or cities now. The last point here is maybe going a bit more in the specific part of what we did here in terms of the work. They often lack accessory zircon, so a zirconium silicate mineral that we very often use for geochronology, especially for uranium lead and also for uranium thorium. And because these alkaline volcanic rocks often do not have zircon, there are actually a couple of very famous volcanoes that we don't fully understand because we do not know how long the magmas are stored under the volcano, where they are stored, how they evolve with time. This is because these alkaline magmas have a very high solubility for zirconium. So the zirconium basically just stays in the melt and never actually crystallizes zircon. And that's why we looked at garnet, as we will see in a minute. So just a couple of examples of these alkaline volcanoes. So this is Pico de Teide on Tenerife in Spain, so an island off the Spanish mainland. And the last eruption was in 1909, producing sort of alkali basaltic lava flows. Then we have here Mount Nyiragongo in the Democratic Republic of Congo, with the last eruption in 2021, probably the most hazardous volcano on the African continent, often with lava flows reaching the city of Goma. Then we have this one very, very famous volcano, Lengai in Tanzania, that we will speak about a little bit later on as well, with the last eruption in 2019, producing carbonatite lava flows. And then last but not least, this is Mount Vesuvius in southern central Italy. So this is a picture taken from a helicopter of the crater, the current crater vent of the volcano. You see already in the background, basically all around Vesuvius, you have the metropolitan area of Naples. So these examples just show that there are a lot of very important volcanoes for many reasons that we should probably study them a little bit more. So just give a quick overview of the three things, or maybe two things that I will talk about. So the first thing is more on the method development part. As you may know, you have downstairs a very beautiful laboratory with a lot of fancy instruments. But a lot of those methods have to first be set up, right? These instruments do not run by itself. It takes a lot of work to develop these analytical methods to run these analyses. So I will talk a little bit about that. And then the first application that was sort of as a first sort of proof of concept that this method is useful for dating silica undersaturated or alkaline volcanic rocks is to date what is called the Ngara-Serra footprint. And we'll see there was a bit of a debate about the age of this unit. And I believe we did not really solve it. Maybe we haven't convinced the people that were working on the stuff enough to accept that this stuff is much younger than they previously thought, as we will see just a few slides on. And then the main part of this talk is about the Garnet petrochronology of a Sommer Vesuvius phonolite. So petrochronology basically just combines geochronology with trace element analysis, isotopic analysis, to look at the temporal evolution of a magmatic system. I'm not sure if we will reach the last point. This is sort of a continuation of the second study where we looked at co-erupted lithic clusts, particularly skarn clusts, so sort of reacted country rock carbonates that get erupted together with the volcanic rocks, and maybe tell us something about the interaction of the magma with the shallow crustal carbonates. But I will first talk about the two first things, and then we will see if we have time for the third one. So this will be the first study that we talk about. The Ngara footprint tuff is located here in northern Tanzania, just on the southernmost tip of Lake Natron. It's a very alkaline lake that is somewhat related maybe to the alkaline volcanoes around. And here you have all the Lengai, just south of the lake, and we believe this tuff is a nephilitic volcanic unit was derived from an eruption of all the Lengai, probably reworked in a river. So it's not an airfall tuff, but it was deposited in a river. And you may see these little bumps in the volcanic tuff. So until a few years ago, this area was covered with sediment and was excavated for these hominin footprints. So of course, these archaeologists were very interested in the age of this unit because it makes a big difference if it's 2,000 years old or 200,000 years old. And it was really entirely unknown at that time. I think the very first abstract that was published about this unit, they were talking about something 100,000 years or 200,000 years. And then they did a relatively systematic study that was published in 2017, where they did quite a bit of effort to date this unit. And it was also covered in National Geographic, and they came up with this little headline that says, "Hundreds of crisscrossing tracks offer a glimpse of life in Africa around 19,000 years ago." And as a geochronologist, you kind of then think, where do these 19,000 years come from? You know, you're kind of trained to not just accept these age numbers as an absolute truth. So we looked at this paper, and it seems like the 19,000 years is actually a biotite argon-argon date. And if you're working in geochronology for long enough, you realize it might not be entirely accurate because biotite tends to have what we call excess argon, which makes the date a little bit too old. And especially in settings like this in the East African Rift, where you have a lot of mantle upwelling and probably mantle component argon in the magmas, this was somewhat questionable. But they also published in the same paper 14 carbon date of around 5 to 6 kiloyears. They somewhat favored an age that was sort of somewhere in between, oddly enough, and interpret the whole thing to be something like late Pleistocene in age, so something like 12,000 years old, 12,000 years old. At that time, we had a PhD student, Anna, who was working on this unit, and he wanted to get a better age. And so we looked at these rocks in a bit more detail and found that they have andradite garnet, so a calcium titanium garnet. And this is a mineral that previously actually has been used in geochronology in two cases. One actually both on Vesuvius. One using uranium thorium helium dating to date an eruption of Vesuvius. Basically, we knew the eruption of Vesuvius from historical sources, but they tried to replicate this historical age, uranium thorium helium age. And this is actually what we tried first on this one. And we absolutely failed. The uranium thorium helium dates were all way older than anything reasonable, several 100,000 years old. So that didn't work. That was done with Istvan Dunkel, who was actually one of my first sort of geochronology lecturers at the university where I studied my undergrad. It was a bit surprising because most people would have not really considered that excess helium, for example, would be a problem in those type of minerals. But it seems like something is making those dates go. So we started to look at this garnets from a different perspective, and that is using the uranium thorium disequilibrium. But it was sort of something we started really from absolute scratch, and we had to first figure out how this works. So we tried a little bit, and ultimately this is sort of the setup that we came up with that we think worked for us pretty well, but there were several things to overcome in the development of this methodology. So if you go I don't know, how many floors down are the labs? 2 floors down. If you go 2 floors down, actually you find all the equipment that we have on this list here. It's very nice instrumentation. It's just nothing super exceptional that only exists in one lab in the world. I can only encourage you to go down there and see those instrumentations and experiment a little bit, because ultimately this has been something that we haven't really planned for, but came about from questions that popped up about the age of this stuff, and then trying to develop a method that would work and solve this question. So it's the Australian Scientific Instrument laser ablation system coupled to thermal element XR ICP-MS, exactly the same instrument that Scott and Karen just showed me downstairs. Because these garnets are much lower in uranium and thorium concentration than other accessory minerals that we typically date, we use just a relatively big spot size. Typically, for example, for zircon that has hundreds of ppm of uranium, you use maybe a 30 micrometer spot diameter. But for the garnets, we use 173 micrometer spot size. A bit of an odd number, just ignore that's roughly 170. That's just a matter of the laser setting. With 173 micrometer spot size, you basically just ablate away any zircon in its entirety, because that's how small they are. But these garnets are significantly bigger. They are millimeter-sized crystals, up to 2-3 millimeter-sized crystals. So this spot size is absolutely sufficient in terms of spatial resolution to also resolve differences within individual crystals. Then this gets a little bit technical, maybe for the students, but there's several sort of analytical problems that we had to overcome. That is a correction for what we call abundant sensitivity of the 232 thorium tail on 230 thorium. That's maybe something more for Scott and Karen. We basically just used a very high thorium mineral, in this case a monazite, to calculate this abundant sensitivity that we used for correction. Then we also had to obviously correct for the elemental fractionation. That is something people know very well for uranium lead when they do that by laser ablation. Uranium and lead gets fractionated from each other, so the ratio that you measure is not the correct ratio in the mineral. The same is true for uranium thorium, a little bit less pronounced because these two elements are very similar chemically. But we did this using basically just a standard matrix matched standardization. And what we used here, and that is maybe somewhat a little bit special, because when you do, for example, zircons, you look for very homogeneous zircon crystals that are basically have a homogeneous uranium lead ratio throughout the crystal. In this case, it was basically impossible to find homogeneous garnets that would be suitable for that. But because we're looking at the disequilibrium between uranium and thorium, we basically just use garnets that are in secular equilibrium, which means the 238 uranium to 230 thorium ratio, activity ratio by definition is 1. So we know that ratio very well, and it's homogeneous throughout the entire crystal. So these were the main points that we had to consider, and then we just basically started analyzing different things. We actually went down to the museum, got a couple of garnets from different parts of the world of different composition, and started analyzing these minerals. Grossular android from Mali, another grossular android. We also did some spessartine, so more manganese garnet that didn't work very well, but ultimately they all plot on what we call the equiline. So the line that indicates isotopic equilibrium between the 230 thorium and the 238 uranium. In this case, just normalized to the long-lived 232 thorium. Yeah. In this case, basically, they just had a much lower uranium thorium concentration. That's the main reason. So this is a relatively straightforward, because we don't need to know the age of these reference materials. We have to know they're older than 400,000 years. In these cases, are very straightforward. We know they're the Mali grossular andradite, for example, it's 200 million years old, and so on. So we knew they are in equilibrium, and we just have to try to analytically reproduce secular equilibrium. And we don't need to know the exact age of all of our reference materials. So this was the first somewhat surprisingly easy outcome, and it was surprisingly easy to get this result. And from there, we were quite confident that this could be used to date the Ngara footprint. The main thing that is important in this case is we are essentially trying to detect 230 thorium. So this intermediate daughter product of the uranium series decay, because it's about 100,000 times less abundant than 238 uranium. And we basically just have to try to be above the limit of detection for the 230 thorium. And here it's plotted against uranium concentration. The two curves here are basically the counting statistics uncertainties for different ratios of 230 thorium to 238. Essentially, we can analyze anything that is somewhat above 1 ppm of uranium. That's the main essence of this. If you go to higher concentrations, 10 ppm, 100 ppm, obviously it gets much better, and we're further away from the limit of detection, and the counting statistics becomes significantly better. One other thing here is when we're looking at uranium lead dating, like what Scott is doing and what I was doing for many years, we're looking at per mill level of uncertainty, right? Because we're looking at very old rocks where a per mill level uncertainty can translate into several 100,000 years of uncertainty on the date. In this case, we're probably looking rather at something like 10%, 5% uncertainty on an individual spot analysis that will still give us enough resolution to resolve things in the last 10, 20,000 years that we were looking at in terms of the age of these rocks. So for the garnets from this footprint tuff, like I said, these were sort of the biotite age and the 14 carbon date. For the garnets from the Ngara footprint tuff, we get this uranium thorium isochron. So this is the equiline here. So if it was in secular equilibrium, all the data points would fall on this red dotted line. So they're clearly in disequilibrium. So they're clearly younger than 300,000 years as a first constraint. But this line basically gives us the age of the crystallization of these garnets, and we get an age of 4.9 plus minus 0.58 thousand years. So about 5,000 years old rather than 19,000 years. And that is actually very consistent with the 14 carbon dates. And even before we did these analyses and read this paper, I would have always favored the 14 carbon date over the biotite argon date. And I think with this, we just confirmed that the 14 carbon date is much more accurate than the biotite. And in a bigger context, this is somewhat important because if it was 19,000 years ago, these hominins that we can trace there by their footprints, that would have been through a relatively dry period in the late Pleistocene, while our dates of about 5,000 years is basically right at the very end of what is called the African humid period, where we had very high lake levels in all of the lakes in East Africa, and basically green Sahara during this. So this gives us a bit of a climatic context of this hominin in Tanzania. So that was the first sort of successful application. And just to give you a few take-home messages about this short study. So I think we can show now that we can date garnet accurately and reasonably precisely. If you talk to Scott, then he will tell you that he can analyze zircons with 100 times better precision. But I think for this type of study, you always have to think about the question that you want to answer and what resolution you need to resolve the question. This is precise enough to answer a lot of interesting questions in the last 10 or 20 or 30,000 years. In my opinion, this footprint tuff is mid-Holocene and not late Pleistocene. I've seen papers that were published afterwards where people still use that 12,000 year age. Maybe they haven't seen our publication. Maybe they've seen it and just ignored it. We did some more analysis, and they come out sort of roughly the same. And I think it's pretty clear that this is a mid-Holocene eruption of the Aldini-Lengai that we're looking at.
The paleontologist is going to hate you as soon as you tell them that fossils are younger than they wanted.
Exactly. I think they don't like me, but that's okay. Yeah. So I mean, I feel like there's not so much to argue about in this case. It's consistent with these 14 carbon dates. I wouldn't really see much of an argument why both of these give us consistently dates of about 5,000 years, and we still prefer something that has been shown previously to be a rather questionable chronometer. That is the biotite argument. And then when we published this, there were a lot of people who were a bit like, well, that's nice, but do we have actually any other volcanoes that have andradite garnet? It's clearly not the first mineral you think about when you think about volcanic rocks. Obviously we do. Otherwise, the presentation would stop now. That is essentially the one that we see here sticking out of the clouds. I call it here Sommer Vesuvius because it's really just a kind of complex. You see this part here is actually the Monte Somma caldera, so the older part of the volcano. And in this caldera, you're growing the current Vesuvius cone. So this would what you would call Vesuvius. This is what you would call Somma, and the whole volcano is called the Somma Vesuvius volcanic complex. And it produces these highly fractionated phonolites. As we will see, they're pretty impressive in their history and very important. So Somma Vesuvius, I think last time I gave a presentation about this in Italy. So the headline was like, this doesn't really need much of an introduction, but I feel like you're much further away from Italy. So I give you a bit more of an introduction about Vesuvius, because it's a very interesting volcano located in the Campanian plain. The Campania is the province in Italy in which Naples is located, and it's in really close vicinity to the Naples metropolitan area. As you see here, this is the volcano, and this is the Naples metropolitan area with more than 1 million people really living around the volcano in central Italy. So it's definitely one of the most hazardous volcanoes in Europe. It's a very, very intensely monitored by the what's called the Osservatorio Vesuviano, so the observatory that is really dedicated to monitoring the volcanoes in this area, because we do not only have Vesuvius. You may have heard about a much bigger volcano also in this area called the Campi Flegrei, the Grain Fields, which is sort of a caldera volcano under the Gulf of Naples. So it's a very sort of vulnerable area in terms of volcanic hazard, and I think there's no other area in Italy that in Europe that could face such big eruptions. If you Google famous volcanoes, it comes up as the first one, just above Mount Etna and Krakatoa, and I think the next one would be Mount St. Helens. So clearly, it's a volcano that a lot of people know, right? And so we published this paper 2 years ago, approximately, and using basically the approach that we just developed on the Tuff in Tanzania, and continued that work. And I will show you now a bit of the results of this. Here you also see again, this is the current cone of Mount Vesuvius with the active crater that is photographed from Pompeii, the Roman city of Pompeii, that was completely covered in pumice fallout of the eruption in 79 AD. Very famous eruption that was observed by a Roman chronicler, Pliny the Younger, And Pliny the Younger, that is basically where we get the term Plinian eruption from. So this is really the type example of a Plinian eruption that covered the whole city of Pompeii and also completely destroyed another city on the coast called Herculaneum. Herculaneum was completely covered in pyroclastic flows and actually resulted in a lot of death, especially in Herculaneum. So these are human skeleton preserved in volcanic ash, in this case, in these pyroclastic flow deposits in the Roman city of Herculaneum. And the last eruption of Vesuvius was in 1944. You see it here. This is the volcano erupting. And these are actually photos taken from the airplanes of the bomber planes from the Allies towards the end of the Second World War. So also a very sort of famous eruption. But so 1944 is now a little bit more than 70 years ago, and we didn't have any eruptions of Vesuvius. And of course, a bit the question is, will it erupt again anytime soon? Could it maybe produce a big eruption like we had in 79 AD and cover large parts of Naples? If you know Naples a little bit, it's a beautiful place, but it's also a very messy city. And evacuating Naples within any reasonable time frame would result in absolute chaos. There's already a huge chaos every afternoon if everybody's going home from work. But if you want to evacuate that would be a pretty big organizational exercise that I'm not sure they're really prepared for. So Vesuvius produced a lot of eruptions in the past. Sort of smaller scale lavas. You don't actually see it here very well. There's intervals with sort of open conduit lava flow eruptions, but it also produced these very big eruptions. The first big Plinian eruption was the Comici di Base. Then around 9,000 years ago, you had the Mercator eruption. About 4,000 years ago, you had the Avellino eruption. And then in 79 AD, you had the famous Pompeii eruption. And you see these sort of intervals that we call repose intervals, so intervals of volcanic quiescence between different eruptions. They sort of get shorter with time. And there are actually volcanologists that always sort of hypothesize that these intervals, for example, between the Mercato and the Avellino eruption here, where we do not see any other eruptions, are actually related to phonolithic magma being present in the upper crust, and no mafic magmas that would otherwise produce these lava flows can actually ascend to the Earth's surface because they just get stuck in the phonolithic magma chamber underneath the volcano. So this is sort of the hypothesis, and it's a pretty good hypothesis because we can test it using Garnet geochronology. So if we analyze the garnets and we can show that the magma was present for that time interval, that would be very good evidence that this is probably a good model in terms of how these phonolithic magmas can also affect eruption dynamics of this volcano in terms of different compositional magmas. The last relatively big eruption is the Polena eruption in 472 AD. It's a smaller subplinian eruption, but also very, very interesting. And these big eruptions here, especially also the eruption from Avellino, you can see they sort of with time become more silica undersaturated. So Polena eruption, for example, the last big one is very undersaturated. The Comici di Base is more trachytic eruption, and then in between the Mercato and Avellino eruption are these phonolithic, typical phonolithic peppers. Yeah, there's four major Plinian and several of these subplinian eruptions, like the Polena eruption. And especially the Avellino eruption from 4,000 years before present is sort of considered in all of the volcanic hazard scenarios as sort of the worst case scenario for any future hazard in this area. So it's certainly a eruption to look at in a bit more detail. I'm not sure if I will get to the last point of the presentation where we look at this eruption in more detail, but we will see already from the initial results on the garnets that this is quite an interesting case. So the objectives in terms of the study on Vesuvius is really first to constrain the lifetime of these monolithic magma chambers of some of Vesuvius, so the magma chambers that really feed these big clean eruptions. How long is that magma present in the upper crust? If we, for example, detect such magma today using seismic images, does that mean it will erupt relatively soon? Or could it actually stay there for the next 5,000 years until it erupts and we don't really have to worry about it? When we combine this with a bit more of a geochemistry, we can maybe say something about the dynamics of these magma reservoirs and what happens between sort of assembly of these magma chambers in the shallow crust to eruption. And then, like I said, if we have phonolithic magmas in the upper crust, it may influence the eruption of more mafic magmas coming from deeper reservoirs, and that would sort of control the eruption dynamics of this volcano. As a last point, we compiled a lot of data that we'll show later and look a bit at the relationship between magma composition and magma storage timescales in these crustal magma plumbing systems. So these are the garnets in the Vesuvius phonolites. M marked here is the Mercator eruption. AV are the garnets from the Avellino eruption. And there was actually a paper published in 2007 already that looked at these garnets in quite some detail. And in fact, they also produced uranium-thorium isotron for the Mercator eruption, but using bulk techniques. So they just took several milligrams of garnet, dissolved them, or dissolved 2 aliquots of garnet, dissolved some whole rock, and made sort of a traditional uranium-thorium isotron. They were essentially not even trying to date the garnets from the Avellino eruption because they're super complexly zoned, compositionally zoned. So they were a bit like, why would we analyze such a heterogeneous material in bulk while we would really want to resolve the differences within individual crystals? Because the Mercator garnets are very, very homogeneous in composition. So this was the first study that really looked at these garnets in detail. And then in 2008, Bruno Skaye and colleagues published a paper in Nature looking at basically they were performing experiments to reconstruct the magma storage conditions based on phase equilibrium. And that's pretty cool for us because we know essentially the phase equilibria or the relationship between the crystallization of the other minerals and the garnets. So some of you may know very well that for zircons, for example, is sometimes a really big problem. We don't really know when zircon crystallizes relative to the other phases. At what temperature do they saturate? What do we really date when we look at the zircon? For these garnets, we actually know pretty well the stability windows under which they crystallize. And so the phonolites that we looked at, basically the Mercator, Avellino, and Pompeii eruption. We also looked at the Polena eruption, but like I said, it's not as important. They are always compositionally zoned pumice deposits, pumice followed. The Mercator is actually very homogeneous in terms of the glass composition. These are the yellow dots here. And like I said, also the garnets are very homogeneous. And we actually basically do not see any variations in the glass compositions. But Avellino and Pompeii eruptions are sort of well known to be very compositionally zoned, always with these early erupted white pumices at the base, and then this layer of gray pumices at the top. Basically, an inverted magma chamber with very evolved magmas at the top, less evolved magmas at the base, or at the base, maybe these less evolved compositions come from mafic recharge into the evolved phonolithic magma chamber just before eruption. And so they are the super highly fractionated monolithic deposits. So these are just the sample localities for all of these samples. This is the volcanic edifice of the Vesuvius. This is how they look like. These are just compositional electron microscope maps. These are all from the 79 AD eruption, because when we started with this, I actually had a very good bachelor student who was doing a lot of work. When I then had to take over myself, kind of skipped the, the sort of tedious microscope work. So we got only very nice images for the 79 AD eruption, but you can already see there's sort of these oscillatory zone crystals like these ones, some with those high titanium cores, and some very, very exotic crystals with these resorbed zones, very strong contrasting trace element, major and trace element compositions in these crystals. And we will see that while this is probably important in terms of looking at the dynamics, it's not actually that important for the uranium-thorium systematics. So these are the trace element compositions. It's all done by laser ablation ICP-MS. So you can do that downstairs as well as we did here. So the yellow ones are the, here you see the Mercator, very, very homogeneous. Like you can do another 50 analysis that will all plot in this little point here. While in contrast to that, the Avellino eruption, Pompeii eruption, very, very heterogeneous, huge range. These are basically small inset rare earth element diagrams from lanthanum to lutetium. So these typical rare earth element patterns for garnets, a bit depleted in the lights, enriched in the middle, and then very, very diverse in the heavy rare earth elements. These little arrows here, these are within single crystals from the core to the rim. So you can go over a huge range in neodymium ytterbium, which is basically the ratio from a heavy to a middle. So it indicates the slope of the rare earth element pattern. So we see this very nicely. We also see this in the Polena eruption here in blue. And what we basically think this means is, first, each of these eruptions was fed from a distinct magma batch. So there was not one long-lived magma reservoirs under the volcano that gets repeatedly tapped to produce eruptions, but you build a new shallow reservoir for each of those eruptions. And interestingly, the garnet from the white and the gray pumice in the zone deposits are actually exactly the same. So I think we just think this means we do not record the last recharge event that produced this compositional zoning in the garnets. So the garnets all crystallized before the last recharge event, and we do not record the last several years before eruption. These are just sort of like profiles through individual crystals. See, they can be very zoned. This is also neodymium ytterbium ratio again here. This for Avellino, this for Pompeii. Interestingly, in the Pompeii deposits, even the very outermost rim of the crystal is not in equilibrium with the glass, which is something maybe you sometimes assume, but maybe you shouldn't be it's probably not the best assumption to start with, because these crystals might have crystallized from a sort of different magma than what you now see in the glass composition. In the white pumices of the Avellino, the outermost rims are actually perfectly in equilibrium with the glass. So what we think this means, again, this sort of confirms that we do not record this last recharge event, but the white pumice in the Avellino was basically unaffected by the recharge event, while in the Pompeii magma chamber, the whole reservoir was affected by the recharge event. So the composition of the monolithic magma was modified after crystallization of the garnet. And this is sort of consistent with the less evolved glass composition. And these are basically what we think this means. The last mafic recharge event did not affect the phonolithic top of the Pompeii reservoir, but it affected actually the other way around. So did not affect the Avellino upper very evolved pumices, but it did that in the Pompeii. The Mercator is a bit of a puzzling one because we don't really see that mafic part of the reservoir, and we don't really know what really triggered the Mercator eruption. There was a recharge event that was maybe compositionally similar to the phonolite, so we don't really see any contrast in composition, but we certainly did not have any mafic recharge that triggered that eruption. So when we now look at the uranium thorium isotope systematics, these are the isotrons here. This is for the Polena, this is for Pompeii, these two for the gray and the white pumices, Mercator down here, and these two here up are for the Avellino gray and white pumices. And you can see for the Avellino eruption, we get ages about 8,800 years or 8,900 years. For the Mercator eruption, we get something like 14,500 years. And for the Pompeii eruption, we get something like 3,000 years. Remember, the eruption ages are basically 2,000 for Pompeii, 4,000 for Avellino, and about 9,000 for Mercator. The precision is really good. For the Avellino eruption, where we get this really big, nice spread in uranium-thorium ratio, we get uncertainties on the order of 200 to 500 years. And for the others, we get uncertainties of about 1,000 years. So we can really resolve these differences between the crystallization of the garnet, so the emplacement of the magma in the upper crust, and the eruption. We also try to, these little light gray ellipses here are actually the outermost crystal surfaces of the garnets, because we wanted to see if they are maybe younger and date the eruption, especially in the Avellino, where they are sort of compositionally in equilibrium with the glass. But they did not. They actually fall on the exact same isotron as the course, so they must have crystallized relatively quickly. And we can't really resolve the difference between the interior of the crystal and the outermost surface. Most importantly, all of these garnets predate eruption by approximately 1,000 to 5,000 years. So we're also now looking at timescales that I don't think there's any study on zircons that can resolve something on that order of 1,000 to 5,000 years, where we're really looking at timescales that become somewhat relevant for us, because it does make a difference if we have a pre-eruption storage of 5,000 years or of 500 years when we look at the future potential hazard of such a volcano. So then we, of course, we had to sort of ask ourselves what would control the garnet residence time if it's sort of like a different between the different eruptions, but always relatively young. So we looked at correlations with erupted volume. So maybe a larger magma reservoir would take longer and reside longer, or maybe a deeper reservoir would reside longer than the shallow. So we looked at a correlation with the storage depth. We couldn't really find any of this. There's no correlation with erupted volume, no correlation with storage pressure, no relationship between temperature of garnet saturation or phase equilibria that we have from the Skye study. So ultimately, we think these garnet residence time really reflect the pre-eruption magma storage timescales, and they're not controlled by sort of, it's shorter for the Pompeii because garnet crystallizes later than in the Avellino eruption or anything like that. I think it basically, the garnets provide us with a direct estimate of the magma storage timescale. And interestingly, the pre-eruption residence times scale with the progressively shorter repose intervals. So that's what we looked at earlier, that we have these longer repose intervals for the older eruption, and we basically now get exactly those timescales for the storage of these magmas before eruption. So with that, I think we can sort of confirm this hypothesis of the phonolites being in the upper crust during these repose intervals and controlling eruption of the volcano. One other small aspect, whenever you do geochronology using isochrons, which is done in many cases, for example, rubidium strontium, samarium neodymium, and so on, apart from getting an age, you also get the initial isotope composition. In this case, the thorium isotope composition. And this can be basically used as a tracer together with the age. And so in this case, we see this sort of like systematic trend towards higher 230 thorium, 232 thorium ratios. This increase here between the Mercato, Avellino, and Pompeii eruption can essentially just be explained by radioactive decay. So starting from here to there, we don't really need any assimilation or recharge. It could also just be the source of these phonolites is evolving through time and is approaching equilibrium in the decay. This one, for this one here, the Polena eruption, for the youngest one, we basically need something else. And I think the best candidate for that is assimilation of carbonates in the shallow crust, because carbonates has very high 230 thorium to 2 thorium ratios, because they basically have no thorium, so no 232 thorium, but they have some uranium, so they also have 230 thorium. So they have very high ratios that can really just go well beyond the scale off the screen, essentially. So you need very little carbonate assimilation to explain this shift. And that's sort of systematic with a shallower storage of the Polena way within the shallow crustal carbonates compared to the earlier eruption. So shallower crustal storage, more assimilation of the carbonates traced by the thorium isotopes. So when we quickly wrap this up, to look at a comparison of what we find at Vesuvius and some other volcanoes. So we basically here compiled data for major phenocrysts and plotted a host magma MGO against magma residence time. Sorry, somehow the numbers are missing here. Maybe they only down here. Okay, let's keep this. So this is 1, 10, 100, and 1,000. So this is on a log scale here. These gray data points are from different volcanoes and subduction zones, different intraplate volcanoes. And then we have data from Vesuvius. This is from the Vesuvius phonotephrites erupted in 1944. So the last eruption of Vesuvius. And we get sort of different isochrons, bulk mineral isochrons from a previous study this is a lucite ground mass isochron, giving us very short time scales at very mafic composition. Then we have here the 1944 lava and tephras at quite long residence times, more than 10,000 years. And up here you have a cumulate, co-erupted cumulate cluster from the 1944 eruption with a residence time of more than 20,000 years. So this cumulate cluster was basically crystallized at the very early beginning of that volcano. So the volcano goes back in eruption history to something like 22,000 years, maybe a bit further. But so there were mafic rocks in probably somewhere in the lower crust that already crystallized much earlier. So what we see here when we compile all this data, the sort of density contours that should be seen here as well, but it doesn't really matter too much. So I marked it here 1, 2, 3. So there are sort of like different regimes of different magmas in the crust. One here would be sort of short upper crustal storage of mafic magma. So basically the last interval of storage before an eruption of a basaltic composition. Then here we have those sort of like prolonged deep crustal storage of mafic to intermediate magmas. And basically here we see that old crystals are scavenged and recycled into younger eruptions. Remember, this is from 1944. So it's basically a very recent eruption, recycling crystals that are several tens to thousands of years old. And down here, we have the short upper crustal storage of the extracted felsic liquids. So very low magnesium content. So these are basically rhyolites and phonolites, and we get these really short upper crustal storage times. And of course, we all worked on zircons for many years. This is all based on major phenocryst isochrons. But we kind of at least wanted to try to see how this looks like for zircons. So we compiled some data for zircons, mostly data based on uranium thorium data, and only data where we would also get host magma magnesium content. And that's sort of what we see here. And it's in the first instance, it was a little bit surprising that we basically get longer residence times with less evolved magma. So increasing magnesium content, we get these longer pre-eruption residence. And I think we did just look at two different domains again. Up here, you have more the erupted crystal mushes, so magmas that are very crystal rich, while down here, where the 2 is, we have the extracted liquids. So basically very evolved liquids that get extracted out of a crystal mush and are stored for a very short time before they erupt. And we only get the crystals that crystallized after extraction of these liquids. And I think we see this also in many other volcanoes. So yeah, some take-home messages about Vesuvius. So the geochronology of these igneous garnets, we think it's a very powerful tool to constrain the magmatic processes under these volcanoes. Unfortunately, there are not too many volcanoes that contain igneous garnet, but at Somma Vesuvius, I think even to study this iconic volcano, it was worth developing these methods. We see discrete phonolite magma chambers that existed throughout most of the volcano's lifetime. So there was phonolitic magma present in the upper crust throughout most of the volcano's life. And the presence of these phonolitic magmas in the upper crust controlled the eruption dynamics by basically preventing the ascent of more mafic magmas from deeper reservoirs. So basically acting sort of as a sponge where you cannot go past. You eject the mafic magmas into the phonolitic magma in the upper crust, and they never come out at the top. The very recent phonotephrite eruptions, so these very recent lavas like the 1944 eruption, they basically sample this long-lived lower crustal reservoir. So at present day, we do not have this phonolitic sponge in the upper crust that would not allow the mafic magmas to ascend. So that probably tells us that a future Plinian eruption is very unlikely without several centuries of volcanic quiescence. So today, if in 20 years from now or 40 years from now, we get another mafic eruption like in 1944, we know the plumbing system still doesn't have any phonolite. We're still sampling the lower crustal mafic reservoir, and we should not be too worried about big eruption. However, if you look at the setting, obviously even an eruption like in 1944 would be quite catastrophic in Naples and for the people that live. And on the last point, this relationship between residence times and host magma composition sort of maps out these discrete storage regimes in subvolcanic plumbing systems. And with that, I think I conclude. That was the hour that I had. So I kind of could predict that the last part would not fit in, but we can look at it maybe separately if you're interested. Thank you very much.
Thank you so much, Jörn. Do you have any questions from the audience?
Yeah, thank you. A great talk. I guess I'm a little puzzled, and I don't know much about magmatic garnet, but my understanding was that that you're going to look for magmatic garnet in per aluminous magmas, not per alkaline ones, where you shouldn't really maybe ever see them. So what's going on there? I mean, these garnets are some kind of solid solution of andradite and grossular. There's plenty of aluminum, shitload of aluminum in grossular. So how is it that these garnets are able to crystallize in such an alkaline melt?
Good question. So clearly, that's first of all, that's the sort of the difference in composition. These are also very titanium rich. So compositionally, they're quite special garnets, becoming more titanium rich even in the less evolved magmas at Aldini-Lengai, for example. I mean, at Vesuvius, yeah, there were a lot of questions. Are these actually magmatic? So the other option would be that they are genocrysts from some post-rock, crustal rocks, whatever. So it's tricky, but we know from the phase equilibrium experiments that if you have that composition of phonolites, you're crystallizing garnet from these type of magmas. So ultimately, it's not. I don't think there's anything particular in terms of what controls crystallization of the garnets. It's just the composition of the magmas. I mean, they're also very calcium-rich pyroxene, then the garnet. So there's nothing really particular. I mean, there have been a lot of discussion around what is the importance of assimilating carbonates for crystallizing these garnets and so on. I think ultimately it's just the composition of the magmas and the storage conditions that these garnets are stable under these conditions and they crystallize in the magmas.
Okay. Let's see. I think of another one. How do you know that in your laser spots you don't have tiny inclusions of other minerals? Zircon would completely screw it up, probably. I saw you mentioned apatite, but
absolutely, yeah.
You didn't mention anything about possible invisible, barely visible inclusions.
Actually, the apatite inclusions are quite important. When you look at the isochrons here, so especially here, the apatite inclusions are very thorium rich. So they have a very low uranium-thorium ratio. So basically, all of these data points down here are basically spots where we have quite a lot of apatite inclusion in the analyzed spot. So to some extent, you could interpret this as a mixing line between apatite and garnet. So, playing devil's advocate, this could also be a scenario where you can have a different thorium isotope composition in the apatites compared to the garnet.
If that's the case, then all of your conclusions go out the window.
Absolutely. Then this is not an isochron, but a mixing, right? I mean, that's a possibility. I think it's a relatively unlikely scenario, considering sort of the how consistent the dates are also with eruption history. I mean, if we would think that then this isochron here, if it was a mixing line, also gives us an age of exactly the previous eruption, probably relatively unlikely.
It's a good point.
Same here, this 14.5 in the Mercator. I didn't mention this because it's something that maybe is a little controversial, but it's actually the exact same. This age is actually exactly the age of the Neapolitan yellow tuff from the Campi Flegrei, so the other volcano just next door. Maybe there's some sort of connections between Vesuvius and Campi Flegrei. Same here, if these were just mixing lines, probably would not get something that is so close in age to the historic eruptions. But it's clearly something that it's an important point to consider.
I got another question from Scott at the back.
Yeah, that was a great talk. I just wonder, based on the CL images or the imaging you did, I guess we don't have to worry about this, but do we have to think about diffusion and in high temperature environments or something? Or, I mean, those, I guess those, you know, the contacts there between the zones look very sharp, right? So maybe there's no diffusion, but.
I mean, it really depends on which element you're looking at, right? I think from diffusion data in other minerals for uranium and thorium, I would probably think it's not a problem in garnet that any of those two would significantly diffuse and re-equilibrate during at temperatures that are relevant here. If it was in much, you know, in the nephilinites, you know, these are hot magmas. There that could be maybe more of a problem. At the same time, maybe it's also, you know, a good thing if we want to date eruption, for example, right? So in that case, maybe it's actually favorable. I don't think it's a big problem, but we do see it for other elements, and it could be something that actually becomes quite interesting because you see in these profiles. So this is actually sort of like a crystal where you have some resorb core with very high neodymium ytterbium and a rim with low neodymium ytterbium, and you really have this sharp boundary in between. If we look at other elements, for example, lithium, it's just flat, right? So lithium is either there was no difference to start with, or it's completely equilibrium. And there could be other elements that could potentially be used as a diffusion chronometer in the exact same crystals. So that could be super interesting, but it's, as you probably know, it's a lot of work to do diffusion experiments, and just using diffusion data from any other garnet will probably not make you very popular amongst the diffusion chronometry community. So probably want to avoid that until there's really good data for diffusion. Whatever good data for diffusion parameters really means can take decades and several studies until there's any consensus value.
Hi, great talk. As a geophysicist, I'm,
Uh-huh.
following this a bit, but I wanted to ask about, does any of this indicate the size of the chamber, or perhaps a more precise location other than upper and lower crust? And or are you combining perhaps with some of the geophysics that's being collected?
So if we're referring to this part, I think I mean, here we can sort of make a statement about storage depth, whatever that really means. I mean, I don't think we can go into really precise values here. There are ways to estimate the storage pressure. Actually, in garnet, and because they have apatite inclusions, there's actually a barometer that uses the lattice strain in apatite crystals included in garnet. So we could actually do barometry on the same minerals in this case. But probably what we ultimately will get is relatively shallow, 5 to 10 kilometers of storage for the phonolites, while these phonotephrites and more mafic lavas, they probably stored much deeper and then only, reside in the upper crust, or very short between they erupt. I think ultimately this really links to geophysics in the way of what does it mean, what we observe today. I mean, if you do seismic imaging today at Vesuvius, you see a shallow crustal magma reservoir, but of course geophysics doesn't really tell us anything about the composition of that magma. So if that composition was phonolytic, that magma was phonolytic, then we would probably have to worry about a relatively big eruption. But then we would not get any mafic lavas out. So the 1944 eruption probably tells us currently there's still mafic magmas ascending through the entire crust and erupting. But it's a bit of a tricky situation because that's also now 75 years ago, right? So over the last 75 years, maybe we start to accumulate magma. And there's seismic evidence for active sill intrusions underneath Vesuvius. And I would probably think these are mafic, but we don't know, right? So if we now have no more eruptions over the next 100 or 200 years, then I would start to worry, right? That would be a point where I think, okay, now we're having a repose interval that is starting to be very similar to the repose intervals that we had before the big eruptions.
Do we have any questions from the online participants? Okay, then. Well, thank you very much for joining us for this Geotalk. And thank you, Jörn, again. So if you have any questions, please feel free to ask him afterwards. But thank you for coming, everyone.
Thank you, Oslo.